later time. And why do I make a mistake? I make a mistake in getting those not because of Newton's laws, but because of the fact that there is always some error in, there can be disturbances during the time of evolution, which is what we saw the last time. Also, there is the inevitable error in the measurement process, that if I measure the position of a molecule and say that it was at t equal to 0, x equal to 5 centimeters, it could be, depending on what you are measuring with, 5.01 centimeters or 5.001 centimeters, or even maybe 10 to the 5 point with several zeros and then a 1, if you are being very accurate. But that inaccuracy multiplies, and that increases very rapidly, and therefore the predictive power, when I have a large number of particles to deal with, is low. So, all right, I mean, these are essentially free, only colliding with each other. So no interactions, so very uncomplicated business, and yet this is not possible. And therefore, I have to resort to a probabilistic description, where the only statement I make is, if I am dealing with these large number of particles, I only ask how many particles with velocity between v vector and v vector plus dv vector, and coordinates r vector and r plus d3r vector, dr vector. So that is the only question that I can ask, that in this r vector, there are n axes sticking out over here, and this is v, or more correctly, as we saw, the p. Right now, I mean, we'll be sort of not too careful about the v and p. I mean, use v and p as equally good alternatives. So R and P, and I start out over here, and off it wanders, this trajectory goes on in some fashion or other. These intersections are only because I'm looking at a section, they never intersect. So it looks like a whole tangled mess, and you only ask the question, how many particles are there in a small box over here? So in this small box, at any given time, how many particles are going to be present? What is the, so in other words, what is the probability of finding the, what is the probability of finding a particle in that little box over there, which obviously is the volume of the box divided by the total volume, but there would be some other factor, not, it is spatially, so far as the spatial distribution goes, the spatial distribution is uniform. But velocity or momentum distribution is not. But the point is, you need to know, that is what you need to know, the probability of finding a particle with coordinates between r and r plus dr, p and p plus dp. So that is what you are interested in knowing. The probability essentially means how many particles, if dn is the particle number of particles in this volume over here, and n the total number, then dn over n is the probability of finding the a particle with velocity between, where momentum between p and p plus dp were. And as I said, as the things move along, they spatially, if they are free particles and there is no potential to bias them, they are going to distribute themselves uniformly in space, but the velocity distribution is something which we will have to find. So this is where we are. I mean, all these last 2 days, the point where we have arrived is that in order to understand the dynamics of 10 to the power 20 particles running around, I need to introduce a concept of probability. It is not possible for me to accurately give you the dynamics. I can only tell you what is the probability of finding a particle in this small elementary volume of phase space. The RP space is technically known as phase space. So in this phase space, this little volume over here, what is the probability of finding? Now, that probability is going to be a function of R and P. The probability, which if I denote the probability by P, then it is going to be a function. Better write a cap P over here, or I mean, go back to go to velocity, which now makes no difference. So the probability as P of R and V, the probability of finding a coordinate R and the velocity V. So that is some constant because the radial part is not there. I mean, the radial part is uniformly distributed in space, is simply some P of V, with the radial part a constant. So this P of V will be our goal to get at this P of V. So that will be the issue for the class today, that this is where we are so far, and I have been forced to abandon, because of the intrinsic nature of the dynamics of a large number of particles, I have been forced to abandon tracking particles in time. I only talk about their distribution. So now you can ask a very difficult question, that how do I know that this distribution is not going to change with time? Maybe right now I look at this distribution and this distribution has a certain form. 1 hour later, maybe the distribution is something else. Who guarantees that this distribution is not going to change with time? That right now is impossible to answer. You just have to take it for granted that this distribution does not change with time until I do something to it. That is, in this room over here, the number of particles, the number of air molecules, that is, I mean oxygen or nitrogen molecules, which are moving around, let's say with a velocity of 100 meters per second, that number is not going to change unless I allow some more air to come in over here with a different temperature or at a different, if I change the pressure, if I change the temperature, if I do something over here, then that number is going to change. But if I don't let the conditions in this room change, then there is no particular reason for this number to change. Once again, all these issues are quite complicated in the sense that, does that mean that if I take a small volume, over here and say that, look, in this volume, there are 100 particles. So I take a small volume and say that, look, over here, there are 100 particles with velocity between 10 meters per second and 10.1 meters per second. So between 10 meters per second and 10.1 meters per second, that is the range that I'm looking at. And I ask, and right now there are 100 particles with. Now, does that mean that if I measure 5 minutes later, there are going to be exactly 100 particles with velocity between this 10 and 10.1? Or measure 1 hour later, will it be between 10 and 10.1? No, that's not the point at all. The point is that this 100 will be subject to change, but small changes. That is, 100 can become 101, or can become 98, or there would be fluctuations in this number. But if I tell you that the number is 100, it means that the fluctuation is small compared to 100. So it is the number. If I tell you that there are 100 particles with velocity between 10 meters per second and 10.1 meters per second, the number 100 is not a constant forever. It fluctuates. It fluctuates because these particles collide, and you don't have that much of a control over this collision process that you are going to be sure that this number would always be 100. It can change, but the point is that the change will be small, and when the number of particles, total particles, is very big, like 10 to the power 20, the change can be negligible. So that is what this constants, when I'm talking about a constant average velocity or constant average this or that, or let's say even the number density, constant number density, the constant means not a constant in the sense that 100 remains always 100. It means that you are going to change, but change only slightly. And actually, when you take the relative change and take the limit of a very large number of particles, then that relative change goes to 0. So this is what the constancy means. Constancy, when I tell you that the number density is a constant in a given volume, the number of particles which you find over here is the same as number of particles you'll find in a same. So that is what is meant by constant in space, that number of particles in this volume and this volume, they are equal volumes, but located over here and over here, the number would be the same. But that's not the point. But it is not that if there are 100 over here, there needs to be 100 over here. That can be different, but that difference is very small compared to the number of molecules that you are considering. So this is something, I mean, this is all to get your mind clear about what it means by having these probabilistic descriptions and so on and so forth. The picture has to be clear that we will be talking about things which we refer to as constant, things which we call time independent, things which we do this and that with. And in what sense? Time is never going to be a factor for a long time in these discussions. And so if time is not going to be a factor, things are constant in time, but things do fluctuate in time. And all those fluctuations are extremely small in a relative sense. That is, I have if I'm talking about a large number, the relative fluctuation when I'm talking about a large number of particles is very small. So that is the meaning of all these constancies and so on and so forth. And every time as soon as we start the calculation business, if I calculate some average value and say that that is the average value and that is what we would measure if we do an experiment. You do it repeatedly, you get, and then the average comes out. Point is, I also need to calculate what is the fluctuation around that average, and that fluctuation needs to go to 0 as the number of particles become very large. So these are, these are general statements now, which will become clear as we go along. But the philosophy, it needs to be understood that when we go ahead and start doing calculations, you should be able to remember that, look, this was what these were the qualitative statements, and now I'm seeing what it meant. So, all right. So back to the Holy Grail, which was that the ideal gas law is PV equal to NKT, and my business is to find PV equal to NKT. So back to looking at how to calculate the pressure. So now this is serious. It is. This is maths which is within your ability, and at this point the actual calculations.
Sir, can I ask something?
Yes, sure.
So by that term uniform distribution, uniform spatial distribution, are you meaning that the spatial distribution throughout will be remaining constant? Means suppose you are taking some
it means that the density of air at this point in the room is the same as the density of air in that point in the room. So then if I take a small volume over here and count the number of air molecules inside it, and if I take a small equal volume over here and count the number of molecules inside it, those numbers would be equal. And then I'm saying that these are statistical equals. That is, if I find 100 over here, then I will still find 100 over here. But there will be fluctuations. At some point in time, this may become 101 and this may still be 100, or it may become 105. So there are fluctuations which happen, but on the average, it is a constant. That is what I'm saying. The density, if the density of air over here was not the same as the density of air over here, then air would have to flow from right to left in order to make the density equal. And that's a process which we will be looking at later in the course. Yeah.
So that means the V and V plus dV you are talking that almost remains constant throughout the room.
Now, I mean, don't you understand that? I mean, that the density here of air is the same as the density of air over there. I mean, I mean, density is very easy to understand, and it is also, I mean, anybody's common sense should say that the density here of air is the same as density here. Yeah, I mean, that is all that is being said. It is being said in terms which are a little mathematical, because the maths is what we are going to do now. But in doing the maths, you cannot lose the common sense. And it's pretty commonsensical to say the density of air here is the same as density of air over here on the average. You can measure it over here and find 1.0. And whatever 1.001, you can measure it over here and find 1.0011. But that's the fluctuation which on the whole will average out and become zero. That somewhere else it could be 1.009 somewhere, and if I average over this whole room, that fluctuation will be zero. So the density, the mean density of air over in this room is a number which I can trust, so long as the temperature and pressure in this room, if I were to take a pump and pump some amount of the air out, that number is not going to remain the same. If I were to have a contact with the external world, which is hotter or cooler, then as the temperature changes, that number will not be a constant. But given the temperature and pressure remaining the same, the dynamics of the particles inside the room cannot change these numbers significantly. That is the picture. So I'm in the business of calculating the pressure now. So I imagine that these molecules are running around inside a room, and I focus on an area dA, a small area dA, so of this wall on this side. So I'm looking at the wall. There is a box which I'm considering, and this is a section of the box that I'm looking at, and of that the right hand side, right hand boundary, which this is not a cross section, but I mean, in the cross section, I have taken the cross section is like this, and I'm just drawing a projection of that on the board. So this is this area dA. When I draw this area extends perpendicular to the board, and I'm talking about what. So what am I in the business of calculating? I'm in the business of calculating the pressure, and therefore I need to, there are these molecules running around, and they exert, the pressure comes from the force that they exert on that wall over there. So what does the force come from? The force comes from the momentum. There is elastic collision with the wall, so there is a exchange of this comes with a momentum v vector, goes off here with a momentum which is v magnitude in this direction, came with a v vector over here. So there is a transfer of momentum perpendicular to the wall that sets up the pressure. So that is what I'm interested in calculating. So I'm interested in calculating the force in the, so this axis is, let's say, the x-axis, and force in the x direction. Just a second, this room is impossible. I have to. দাদা শুনে যান। দেখুন তো, এই ঘরে এসি চলে না, এটা কি মানে এখানে রোজ 1.5 ঘন্টা করে চিৎকার করা যায়? মানে এটা বললে পরে কোনো কাজ হয় না, রোজ সকালে এসে একটা কি যন্ত্র দিয়ে অন করে দিয়ে চলে যায়, ফাজলামি। আচ্ছা, এই ঘরের এসি চলে না, রোজ এসে সকালে একটা কিছু যন্ত্র দিয়ে কিছু ইয়ে করে যায়, কোনোদিন একটা 3 নম্বর দিন চলছে, কিচ্ছু হয় না, যেরকম গরম ঘর সেরকম গরম রয়ে গেছে। আচ্ছা, ও চললেও কিছু হয় না, রোজ অন্যদিন এসে চালিয়ে দিয়ে যায়, কিচ্ছু হয় না। হাওয়া তো বেরোচ্ছে না, সেটাই হচ্ছে। এটাই রোজ হয় যে ওটা চালালে পরে কোনো হাওয়া আসে না, কে বললে পরে কোনো লাভ হয় না। ওই কার এখানে মানে চার্জে থাকে, মানে তা, হ্যাঁ তাকেই তো, তাকে তিনি রোজ এসে একটা বাটন টিপে চলে যান, মানে তারপরে কিছু হয় না, তারপরে বললে পরে আর কোনো কাজ দেয় না। All right, so it's the force in the x direction that we are desirous of calculating. So I want to look at every collision. So every collision with a particle which has a x component of velocity as v of x. So results in a transfer of momentum, which is 2mvx. So every collision, every time you make a collision, it was vx coming in this direction, it is minus vx, elastic collision, minus vx going in that direction. So mvx to minus mvx, the change is 2mvx. So each collision with the wall over there is going to result in. So what do I need to do? I need to look at this tube over here. So I need to look at this tube over here and find out how many molecules have x velocity v of x. And I call this number nvx. So as I said, that there is a distribution of velocities. So there are this number with velocity between v and vx and vx plus this another number with between 100 and, so if I look at if I take 0.01 as the unit, then between 1.01 and 1.02 there are certain number of molecules. Between 80.01 and 80.00 there are certain number of molecules. So you look at, so nvx, that is the number of molecules, the number of molecules which have a velocity vx, which means between, when I make a statement like this, have a velocity vx, that is between vx and vx plus dvx. So that is, I mean, you have to sort of, every time we are not going to say this, but in this course, when I talk about a number of molecules having a x component of velocity vx, it means that the number which has a velocity between vx and vx plus dvx. So that is the number which one is talking about, and it is, this is n of vx, and that is what we don't know, and we will write this answer, we will get the pressure in terms of this. So how many molecules are there between, so how many molecules have a x velocity between this and this? So this is per unit volume, it is nvx. This is how many molecules? This is nvx, and this is per unit physical volume. That is the number density. It's the physical volume, number per unit volume, and therefore the actual number over here, this is the number density. For actual number, it has to be how many molecules, which, and now I'll make the constraint that which can strike dA in unit time, and that will constrain the length of this to be Vx. So if the particle was over here outside this range and did not and had a the velocity Vx, it would not be able to strike this in unit time. So x component of velocity Vx sitting over here would not. So it is only in unit time, only those molecules which have a velocity between Vx and which have a velocity between 0 and velocity Vx and Vx plus dvx, is only those, though that number nvx, all sitting inside this element over here, would be able to strike the. So the number is going to be n times n of vx times vx times dA. So that would be the number, except that I have to get a factor of half, because half the particles, so it has to be those with a magnitude of velocity vx, and only those which are going to the right. So you look at the a number of molecules with a velocity vx, that number nvx would obviously depend only on the square of vx. It does not, that number is not going to differentiate between vx and minus vx. So when you get this number finally, this number would depend on the square of vx, and therefore only half of those, anticipating that only half of these would be traveling to the right. So half of the nvx go to the right. These are the number of collisions that happen per unit time, and each collision involves a momentum of 2vx. Each collision involves a momentum transfer of 2vx, and therefore the momentum transfer is nvx into half into vx into 2mvx dA. So this is the momentum transfer per unit time, which is m vx square n of vx times dA. So momentum transfer in the x direction per unit time is given by m vx square nvx times d of a. So this is the answer that we were looking for. So the question is, are you with me up to this point? Or do all of you get the, because now it's calculation and it is important that every step is understood at when the step is done. Are you all satisfied with what you see over here?
Yes, sir.
Sir, can you please
Yes,
explain once why the half comes?
Yeah, go ahead.
Sir, can you please explain once why the half comes? Means I could not understand.
Why the half comes?
Yes, sir.
Half comes because the n of vx is going to, that's a number of particles which have a x component of velocity vx. You can easily anticipate that this number, when I calculate this number, it is going to be there would be as many particles which have a minus vx velocity and a plus vx velocity. Therefore, when I calculate n of vx, it would be something which is a function of vx square. So I therefore anticipating that n of vx when calculated would be a function of vx square, then the point is I would explicitly have to write a half, because n of vx will not differentiate between vx being positive and vx being negative. it will turn out to be a number which is proportional to Vx squared. If it were not, things would be, you can, there would be a strong biasing in the system, and that would not be, there is no reason for that to happen. So if there are no biasing forces, things would have to be, the number of molecules with velocity Vx would have to be the same as the number of velocities with the number of molecules with a velocity minus Vx. So when I calculate n of Vx, it would automatically turn out to be a function of Vx squared, and anticipating that, I put a half, because that function of Vx squared will have both kinds in it, those traveling to the right, those traveling to the left. And I am interested in only those traveling to the right, and therefore the factor of half. So, all right. So this is the momentum transfer per unit time.
Sir, so are we basically considering only particles with the magnitude of the velocity in x direction to be Vx, or are we still with velocity? Because
Particles, what are we considering?
With the magnitude of their velocities to be maybe mod Vx.
Yeah.
Are we considering like that? I mean,
sure. I mean, see, the point is that whatever, I mean, what would, if n of Vx turned out to be proportional to, carries a factor Vx, which is, so number traveling to the right, traveling greater or lesser than the, that would not be, I mean, you would not physically expect that to happen, right? So any n of Vx has to be a function of mod Vx. I mean, any physical n of Vx has to be only dependent on so that's, it's not possible for it to depend on Vx. The biasing, there is no biasing in the setup. So number traveling to the right is the same as number traveling to the left. So n of Vx has to be a function of Vx mod, and the magnitude of Vx, and therefore in the anticipating that, I need a half over here.
okay, sir. Sir, I had a doubt from last class. Should I ask it now or towards the end of the class?
About?
From last class. I had a doubt from last class. Should I ask it now or towards the end?
Go ahead and ask what? Yeah.
So you said about a scenario in which a man stands at the door and we have multiple discs. So I wanted to ask, won't the man actually affect each of the discs? Because we have considered the gravity's effect only on the first disc.
What will be affected? Sorry, couldn't.
Sir, we haven't considered the effect of the gravitational force by the person standing at the door.
Gravitational force. No gravitational force over here. Gravitational force is worse than zero. I mean, as close to zero. Imagine two protons. Gravitational force, I mean.
No, sir, we are talking about that scenario from last class. That's why I asked. Should I ask you now?
We are considering
the scenario from last class.
Oh no, all right, sorry. That scenario was simply to drive home the point that even something as weak as a gravitational force, which I have dropped, can in the long run not give me a deterministic dynamics. So I have made use of that. I have got into a probability distribution because of the fact that just gravitational and even then, mind you, it was not a gravitational, it was a 80 kg man, not 10 to the power minus 24 kg proton, right? I mean, so that was, and what you are looking at over here are particles which are, so their interaction potential, which is the gravitational, that is, it is the electrical potential is far bigger. I mean, the fact that these molecules carry dipole moments and there are dipolar interactions between the molecules is infinitely bigger than the gravitational. And for the moment, we are even ignoring those. Yeah.
Okay, sir.
Right. So, yeah, I mean, so the point is that, yes, it is, this is the momentum transfer per unit time. And so the pressure from molecules between having velocities between Vx and Vx plus dVx is, you divide out, this is the force, momentum transfer is the force per unit area is the pressure. So it is mVx square nVx. And to get the total pressure, I have to sum over all possible values, all values of Vx, mVx square nVx. So that's, now comes the next interesting point. So this is so here is the answer, that it is a sum over all Vx and mVx square nVx. nVx is the number of particles with a velocity lying between Vx and Vx plus dVx, which is equal to, so n, which is the total number of particles, summation m Vx squared nVx divided by total n. And this is the probability of a molecule having x velocity between Vx and Vx plus. So this is equal to, so all right, still go one more step, summation m Vx squared p, the probability of Vx, and therefore it is equal to, so now Let me raise this over here, and this is n. Where am I? Yeah. So this is n times, it is Vx square PVx. This is the summation is over all values of Vx. And therefore, this is by definition n times m and average value of Vx square. Now, I'm not sure whether you are whether you have done any probability or not, but even if you have not, I mean, look, this is the probability. I mean, just picture it as this is a probability distribution of V of x, and if I have a probability distribution of, say, some quantity x, then the average value of x, so x lies, let's say, between minus infinity and plus infinity, the average value of x is going to be x px dx, going from minus infinity to plus infinity. So if probability of finding a value of x is given by p of x, finding a value means a value between x and x plus dx, then average x square is similarly minus infinity to plus infinity x square p of x dx, and the average value of any function of x would be minus infinity to plus infinity f of x p of x dx, right? I mean, so that's nothing other than common sense, essentially, that p of x is I don't know what the exact value of x is, but I'm simply telling you that the probability of finding a particular value of x is given by this function p of x. Now you cannot talk about a definite value of x. You can only talk about an average value of x, or for any function of x, you can talk about only its average values. And the average values are defined as, if it's average value of x, take x, multiply by the number of times that value of x occurs, which is this, and sum over. So the fraction with which you see a particular value, you multiply by that and sum over all such quantities, and what you get is the average value of x. And similarly for any other average value. And by that token, the average value, this quantity over here that we have got, is n times m times v average Vx square. So now x, the kind of problems that we will be dealing with most of the time, there is no difference between x, y, and z. So whether I did the calculation along the y direction, or whether I do the calculation along the z direction, I should always get the same answer. So average Vx square is equal to average Vy square is equal to average Vz square, and therefore is equal to 1/3 of Vx square average plus Vy square average plus Vz square average. And this is average value of V square, and that is that. And consequently, this answer is equal to, this is equal to m times n times V square by 3. So this is what this is. Do you get the Are all of you up to this point?
Sir, can you please briefly explain how that 1/3 came? I mean,
How the
1/3.
1/3?
Yes, sir.
Oh, see, Acha, all right. I mean, since there is no difference between the directions X, Y, and Z, if I calculate average value of Vx square, that same would be, I mean, instead of considering collisions in the X direction, if I considered collisions in the Y direction, then you would get the answer as Vy square over here, and the pressure on the X wall is the same as the pressure on the Y wall as the pressure on the Z wall, right? I mean, if this did not happen, then the box would become somewhat deformed. So when everything, I mean, is sort of in equilibrium, the shape is static in time and everything is going all right, the pressure that you have, whether it is in the X direction or Y, because all that I need to do is call X, Y and call Y. I can very easily do that. So that is so far as the velocity goes. I mean, the box can be in shape like a rectangular parallelepiped, but that is not what, I mean, there, of course, we have just simply said that the number density is uniform all throughout. So we have got rid of that. But so far as the velocity goes, the velocity distribution, whether it is a question of Vx or Vy or Vz, that is going to remain the same. I mean, the number of molecules which are having a velocity in the X direction between 100 and 100.1 is the same as the same number as those which have a Y velocity between 100 and 100 plus 1, and the Z similarly with the Z, because so far as the velocity goes, all the X and Y and Z are equally, that there is no difference. I mean, I have no forces acting in any direction, so I have a free particle, whether it is moving along X, moving along Y, or moving along Z, and therefore the velocity distribution is independent of whether I'm talking about Vx, Vy, or Vz. And therefore, when it is a pressure on the in the Y direction, then the answer would come out to be Vy square, and the pressure of the air, the pressure which the air exerts on the wall in this room, for example, is the same pressure everywhere. That is, the pressure inside this room is uniform. So it is the same pressure on that wall, on the ceiling, on the floor, left-hand wall, right-hand wall. So that is what is being said. Yeah. So I am giving, yeah.
So
yes.
my question is that you are considering at first, suppose the velocity of particle in X direction, and
I'm considering what?
Velocity of particle in X direction. You first assumed that, and you said since the coordinates are means it can have in Y direction as well and Z direction as well, so they are equal. You said that initially. No.
I'm not following. The statement being made is that so far as the XYZ dependence is concerned, I had said that the density is uniform.
So there can be collisions between
uniform physical density of the air in this room, which is a question of how many particles of air in this volume and how many particles of air in this volume. But now I'm looking at, take any given small bit and asking how many particles are moving in the x direction, how many particles are moving in the y direction, how many particles are moving in the z direction. And I'm now making a much stronger statement that those numbers are also equal.
But in the mixed case, means when you are considering all the particles, there can be some collision between particle moving in x direction and particle moving in y direction. There can be xy collision, sorry, xz.
All right, do you think the pressure in this room or in the room where you are sitting, the pressure at different parts of the wall are different?
No, sir.
No. And
Yes.
you understand that the pressure is given by this formula over here?
Yes, sir.
And you understand that if it was the pressure on the y direction, y-sided wall, the answer would be the same with Vx square as replaced by Vy square?
Yes, sir.
And then if you understand that the pressure on the x wall is the same as the pressure on the y wall, you have to understand that Vx square is the same, average is the same as Vy square average. Not that Vx square and Vy square are equal. It is the average values which are equal.
Yes, sir. I am stating that means there can be some collisions. Means is the collision taken into account by this average?
No, I don't. Unfortunately, I don't understand what you are saying. Partly because of the audio is not very good at all, so it is very difficult to. I'm not able to decipher the words very well. But the point is that I understood that you have some difficulty in going from this step to this step over here.
No, sir.
And
No, sir. No, sir.
No.
No, not in that step. I'm telling that suppose in a scenario, the particle will be moving in x, y, and z in the all three directions. Means in a general case, not in some particular case that particle are moving in x direction. That in that case there will be collision between x, y, and z direction. But there will always be some collision between the particles moving in x direction and the particle moving in y direction or z directions. Means, sir, am I able to confirm my question?
What that if you were moving with a velocity v, you would see a difference? Are you saying that if there is an observer?
No, not I am moving. So the particles moving in the x direction and another particle moving in y direction, if they happens to collide, are we taking those collisions into account?
Sir, I think he's asking if internal collisions are being taken into account between collisions between molecules.
Collisions are all elastic collisions, which are three-dimensional elastic collisions. So they are what is that is what is giving rise to the equilibrium distribution. And the point is that you are talking about after all those collisions have been taken into account, we are saying that I have a distribution which is determined only by v square. So all collisions have been used only to set up this probabilistic description. Collisions, as I said, the collisions between molecule, obviously the only collisions we are talking about are elastic collisions, and that it is also true that you are treating the collisions change the directions, and but the effect of for all practical purposes, we are talking about a set of non-interacting particles. The explicit effect of collisions have, all right, yeah, I get at your what you may be driving at. The explicit effect of what collisions do to you is not being taken care of in that sense of the word. That what is being assumed is that these are non-interacting particles. They have no, sure they collide and they reflect from each other. But the dynamics of that reflection is not entering the discussion at all. It is for all practical purposes, free particles, completely unbiased in spite of the collisions they undergo. Collisions are important to establish the equilibrium and to make sense of what is going on. But the picture, the distribution that we are looking at is a distribution of free particles. Free particles meaning that I am ignoring, for calculational purposes, all interactions between the particles, what kind of collisions they are undergoing, what kind of interactions they are undergoing, are completely suppressed. So far as this statement goes, these are completely non-interacting particles. There are collisions taking place, but I am not at all bothered by the fact that those collisions can change anything. So it is even in spite of the collisions that are taking place, the statement is that it is a non-interacting set of particles. Any interaction, see, interactions which are collisions are obviously, I mean, of electromagnetic origin. The particles colliding with each other means that they come very close to each other, and then the electromagnetic forces repel them away. So that is what the whole point is, that there are these very short range forces which are going to repel particles away, and those are being ignored. Your long range interactions which hold it together, they are being ignored. Point particles, no question of scattering in in the way in which you are thinking of. These are point particles which we are talking about, and completely free from any interaction. Yes, I mean, when we go into a question of talking about interactions, which would have to be, which would be much later in your the issues of this kind, what you are talking about, would have to be explicitly discussed. All these are very small effects, but and also obviously very difficult to calculate what kind of collisions giving rise to what. But for the moment right now, let me make, these are all point particles that we are talking about, and these point particles are just moving around in this space independent of each other, and they are moving randomly with velocities, with velocity components vx, vy, vz. We are not asking why, we are just saying that that is what it is, because as we said, that if I'm going to use Newton's law and have a collision take place, which I mean in real life would, I am forced into a non-deterministic, that is a probabilistic distribution. But now, having taken that probabilistic point of view, I am saying that these are simply point particles which are moving around, no interaction between the particles. They are moving absolutely independent of each other, and therefore Vx square average, Vy square average, and Vz square average are the same. Yeah, get the picture? Get it?
Yes, sir. Yes, sir. Thank you, sir.
So no interactions at all when we are putting this constraint over here. No question. These are all now point particles which are moving around. We know that all that we have done, and they are moving around randomly. That's it. Point particles moving around randomly. The previous lectures were, why do I have to think of them as random motion rather than, and that was for that I explicitly took a situation where one particle moved around and collided with others. Mind you, I took a absolutely simplified situation where all of them were static, and one except one which moved around and had elastic collisions. A completely toy setup, but a toy setup simply to make the point that even in this toy setup, predictability can be lost. And therefore, a probabilistic description is called for. Having said that a probabilistic description is called for, I'm now talking about these particles which really have no extension. So these particles are virtually point particles and therefore completely independent of each other, independently moving around in the with random velocities, and therefore we can confidently make the statement that this is the ideal gas. That is what the ideal gas is all about: n point particles moving around randomly, and therefore Vx square average, Vy square average, and Vz square average are the same. Yeah, all right. So that is what was bothering you. Get the point. Yeah. And what the picture that you have to have of the ideal gas is just n particles, point particles moving around, each of them in random motion and not interacting with each other in any way whatsoever. Yeah. So there we are. It is then your Vx square, Vy square, Vz square are the same, and it is nm Vx square, which is 1/3 V square average. So then where was I? It was a question of calculating the pressure, and so this pressure is what was being calculated, and this has now become, this is equal to 1/3 m n V square average. So that is, so this is equal to, so the pressure now is 2/3 mn V square average by 2. Dimension, question of just a sec, a dimensional issue over here. It is the number, that is the number per unit volume. So I did a, this was the number of particles in that, which is the and that got multiplied. Sorry, should have, yeah, that got written the dimensions out clearly. NVX is the number, but this number of particles with velocity between x velocity between Vx and Vx plus dVx is actually, I mean, the number, it is not really the, we were to get, the number was really, the number was obtained as this. We got the number by doing NVx times Vx times dA. So actually the status of this is not the number, but the number density. So this is really, I mean, I should have been careful about that. This was actually a volume. So this is number density, which should have, yeah. So I should have been clear about that. So it is, this n is a number density. So when I write the total number over here, it should have been a number density, which is n over v. The dimensions were wrong. So that's why now I have woken up to it. So 1/3 v. Yeah. So very good. So this is dimension v. So it should have been a number density rather than the number. So that's it is. So P is this. So it is 2/3 and mv squared by 2. This is where the free particle business comes in. The energy of the gas is given entirely by the kinetic energy. So this is where you see firsthand that this is 2/3 n over v times epsilon, the average energy of a single particle. So this is the average energy of one particle. So average energy of one particle over here. So, and this is that. So now you see once again the issue that was being talked about, that no interaction among the particles. So no interaction among the particles. These are all free particles, point-like, moving around. The only energy is the kinetic energy of these particles. Any question of altering these, I mean, nothing can alter the kinetic energy of a single particle as it goes along. So it is the interactions, there are no interactions with other particles which can do things to it. So if it did, then I would have to include a potential energy. So technically, I mean, you are considering a completely independent, randomly moving set of particles. The motion of each one of them is random as you go. It's randomly fixing X component, Y component, and Z component. So therefore, I mean, it is this which E, and n times this small epsilon becomes the total energy of the gas. No contribute, it is entirely the kinetic energy of the gas. And you have, at the end of the day, that PV is equal to 2/3 E. So that is what the calculation, that the picture that we have developed for this gas over here, essentially these n free particles moving around randomly, so that there is we need a probabilistic description of the system, because there are these n particles moving around, and the reality is that they would collide, and that collision process would give rise to motion which is not deterministic, and because it is subject to change by the any a small change in initial condition would change it very strongly. So the point of you have to learn to live with this anomaly in thinking, that if I have a set of n independent particles, a set of n independent particles moving around, which are not interacting with each other, there cannot be a distribution. I mean, each one of them, if their velocity is prescribed at t equal to 0, would move along and have the same velocity forever, for all time to come. But the statement being made over here is that I have a random distribution of velocities which these particles have, and they are non-interacting, and yet there is a random, they have somehow managed to randomize. The randomization is always through some kind of an interaction, which essentially is the collision process between them. But collision process between them would suddenly change the velocities and make them go in a different direction, and so on and so forth. But once I have taken that into account, that the physics of it, the evolution is determined because the evolution happens and the equilibration happens because these are interacting particles which are colliding with each other, and so on and so forth, and equilibrium. But once this distribution is set up, I now can switch off all the interactions, and it is being assumed that these are point particles simply moving around in this box over here, not colliding at all, but each of them, they are randomized in the fashion, in the sense that if I look at any small volume over here, in any small volume, you will find all kinds of velocities sitting with a certain distribution which we are going to get. There is some distribution of velocities which holds for every little volume over here. So every little volume of the box has a distribution of velocities which is independent of space, and that was brought about by the interaction process. And once it has been, I mean, sort of brought into account, I simplify life for myself by imagining that these are all free particles, and once they are free particles, I have this distribution which is not subject to change anymore. So that is the picture, and that is the picture which gives rise to this relation where PV is 2/3 E, and E is only kinetic energy and nothing else. So PV equal to 2/3 E is what? But we were after PV equal to what? The point was PV is equal to NKT. So we have to go from here to here. So the first step has been taken. We have come to this point, and we have taken another step that we have said that the velocity has a distribution. So velocity has a distribution. So the velocity has a distribution. There is some p which depends on v square. So there is a p of v square because I have assumed that x, y, and z directions look the same. So not everything is isotropy is the word that one uses. So isotropy essentially means that things are the same in the x, y, and z direction. So whatever happens with Vx happens with Vy, happens with Vz. So V square is the determining factor, which is Vx square plus Vy square plus Vz square. Nothing can depend on the direction of the velocity. It is all determined by the magnitude of the velocity. So P of V square, there is a probability distribution. We have assumed that it exists. We have also assumed that the P of R is a constant, and that has gone out of the picture. It should have been a R and V square, but the R has been taken to be a constant. The density, the number density is uniform, and that is but it is the velocity distribution which is velocity which has a distribution, and that distribution is showing up over here, that the pressure involves a square of the average of the square of the velocity. So it is 1/3 m times the number density times v square average, and therefore the next task is calculate this and obtain this. So that is what the next class is going to be. This establishes that PV is equal to 2/3 C. That we have gone through. What we have gone through is so far the necessity of a probabilistic description, and then the question of, if I have a probabilistic description, then I can use that to calculate the pressure. So if I use a probabilistic picture to calculate the pressure, this is the answer. Having said that this is a gas of point particles, non-interacting completely, no interaction with between the molecules which are point particles. And now the next thing, in tacitly what has come is because of the large numbers, there is a probability distribution, and the large numbers gives rise to problem with Newton's law. With any interaction that you can imagine, you would eventually have a problem with Newton's law telling you that it is very sensitively dependent on initial conditions, and therefore it is intrinsically random. And so the intrinsic randomness means I have to talk about velocity distribution. And now it has to be that I need an actual formula for this velocity distribution. So that is what we will be doing in the next class. This is this is a good place to stop. If you have any, if there is any further clarification that you need on this, I can, well, the next couple of minutes, we have run out of time, but if you have the next couple of minutes, if there is anything which still seems very bothersome, we can talk about. There are issues, yeah, the issues are complicated, and therefore it is worth thinking about, and you can go ahead and ask. Or what, I mean, probably the better thing is, you must be having a class, that next day before we start, on Thursday, think about what are the issues which are